My topic is harmonograph. What is the harmonograph? This, or this. It is amazing, right? And how to draw it? It is a machine with a pen, a paper, and 3 pendulums. Let's watch a video to see how to draw it. You can see that the pen is controlled by 2 pendulums and the paper is controlled by another pendulum. And you can see that the pen draws a harmonograph. And why I choose it? Because I love beautiful pictures and harmonographs are amazing. Then let's have a joke. Debugging is like being a detective in a crime movie where you are also the murderer. Let's talk about the simple pendulum. The tensile force is equal to mg cosine phi, and F is equal to minus mg sine phi, and it is equal to ml times the 5-second derivative. Then we get a differential equation. 5-second derivative plus g over L times sine phi is equal to 0. And we know that for small phi, sine phi is approximate to phi. So we can simplify the equation to F equal to minus ng times phi, and phi is equal to x over L. And we know that a constant times displacement is the simple harmonic motions equation. And then let's see the differential equation again. We replace phi to x over L and simplify the equation, and we get a new differential equation. X second derivative plus g over L times x is equal to 0. And we solve this differential equation, and then we get that the x is equal to ay cosine times this and a2 sine times this. And we can observe that these two coefficient is the same. So we can combine the cosine and sine into a new sine function. And to sum up, the displacement of a pendulum can be read as a sine function. Let's talk about a simple type of harmonographs, the Lissajous curve. Maybe you have seen this in the physics lab. And let's talk about how to generate it. First, we can use the function generator to generate 2 sine waves with different frequencies. And then set the oscilloscope to XY mode. And you can see this graph. The equation of the disastrous curves is these two sine functions. You can observe that the sine function is with different frequencies, and maybe you can assign it with different amplitude, and phi is its phase. And with different ratio of the frequencies, it can generate different curves, and with different phi, the graph will become different shape. Then let's talk about the general harmonograph. In the general case, we should take frictions and air resistance into consideration. And let's see the equation. You can observe that we add the exponential into the equations. dx and dy is the damping coefficient. And let's see the meta simulations. It is the code. N is the number of points, and A1, A2 is the amplitude, and W1, W2 is the frequencies, and D1, D2 is the damping coefficient, and P2 is the phase. These two that define the equations, and this that set the range of the axis, and we plot the two consecutive points with a line, and let's see the demo video. With the time, the amplitude becomes smaller and smaller, and it is exponentially decreased. And let's see the graph with different parameters. First, we see the different frequencies. This is the 2-to-1 graph, and this is the 4-to-1 graph, and this is the 6-to-2 graph, and with smaller amplitude and with different phase, and with smaller damping. And let's see some more complicated graphs. We add the cosine function into the equations. This and this and this. And let's have a joke. Will you marry me? No way. Shouldn't will you marry me? Then let me show you the most interesting part, practical realization. I use the y-suspended pendulum to simulate this harmonograph. You can see that this is my device and my material, and this is the actual device. And let's show you the video. And this is end of my final project.